In terms of the calculus that you will do at year 11 level, especially the integral calculus, which is everything that we've done so far, one of the main applications is this idea of optimization. And we've discussed this in class, but just a reminder that optimization simply means finding the maximum or minimum value of a function. So often this is found when the first derivative is equal to 0, but not always. And here's a tip for new players. The maximum minimum doesn't always occur when the first derivative is equal to 0. Sometimes you've got to consider any domain endpoint. So if you've got a domain restriction, you need to consider the value of the function at that domain restriction. Now, there isn't any one particular method of solution, but this set of steps for problem solving, if you apply those systematically, that'll get you a long way towards solving most problems. You can all read those for yourself. I'm not going to go through them now. We will go through them in the context of a problem. Something else that you might need to be aware of is that when we're optimizing features of physical objects, it's usually something like an area or a volume or something like that. So you might need to remind yourself of some of the basic rules of surface area and volume of shapes. For example, if you happen to be doing, I don't know, an assignment on the surface area of a cylinder, then you would need to be familiar with those rules. All right, let's do some examples. Example 11.1. Suppose you had 102 meters of fencing to make two side-by-side rectangular enclosures. What's the maximum area that you could enclose? So the first step is read the question, read what it says, not what you think it says. So we're actually trying to calculate the maximum area. Step 2 is to draw a large, neat diagram, name any unknowns, and include any relevant information. So we've decided we've let the width be W and the height be H meters. And it's two rectangular side-by-side enclosures. So we've got two rectangles, each have the same width and the same height. And we've got this restriction that the total amount of fencing material is 102 meters. So we just write that down so that we don't forget it, basically. The unknown that we're trying to calculate is that maximum area. You don't have to write that down, but it does help. All right. Step 4, we need to find the equation that we're going to optimize and our constraint equation. So the equation we're going to optimize is always connected to the thing, obviously, that we're optimizing, and we're optimizing the total area. We want a maximum total area. And the equation for that in the super mega basic form is just the width times the height. So start with that. We also have this constraint equation that we've only got 102 meters of material, and that has to make up 4 widths and 3 heights. 1, 2, 3, 4 widths and 1, 2, 3 heights. So write out your constraint equation in its most basic form. Step number 5 says express all unknown quantities in terms of a single variable. It doesn't matter which one you choose, as long as you pick one and stick with it. So if we rewrite the constraint equation in terms of, to express it in terms of width, so we've got 4 width plus 3 height equals 102. 4 times width is 102 minus 3h. Width is 102 minus 3h on 4. So now we have both our variables in terms of a single unknown. Height is height, h, and width is 102 minus 3 lots of height divided by 4. So now we go to number 6, which is to apply the rule, and specifically it's the rule that or the equation that we're trying to optimize. So start with the super mega basic rule. The total area is the total width times the height. The total width, and we can see this very clearly from our diagram, is actually 2w, what we've designated to be w, and our height is h. We know what W is. Here it is. We calculated it up here, or 102 minus 3 on 4. So we substitute it in there. And you can see now that we've got a single equation for area with a single variable, which is height. So all we do from there is tidy it up and simplify it, and we're left with 51h minus 3 on 2 height squared is our area total. Because we're optimizing, question part 7 or step 7 is find the derivative and let it equal to 0. So if this is our area, then we can find our derivative. The derivative of area is 51 minus 6 on 2h. From there, we set it equal to 0 and solve for h. H is 17. So when height is 17, the area is, we sub it back into our equation, into this equation here, and we get that our area is 433.5 square meters. Step 8 says evaluate the reasonableness of your answers and apply any conditions. This is a reasonable answer. What you're really looking for is any negative or non-real answers or any answers outside the specified domain. We don't have a specified domain. Our answer is positive and real, so we can keep it. Step 9, read the question again. Have you answered the question? So the actual question is, what is the maximum area? And we have calculated the maximum area. Step 10, wordy in, wordy out. The maximum area that can be enclosed is 433.5 square meters. And that's it.